of what we talked about on Friday. Okay, we talked about the law of conservation of mechanical energy on Friday. And what that says is that the initial mechanical energy of an object equals the final mechanical energy of an object, provided no work is being done anywhere in between. Okay, the energy of an object cannot change if no work is being done. All right, energy can't be created, it can't be destroyed. Okay, that's what we're looking at there. The other thing we learned is that mechanical energy is the sum of potential energy and kinetic energy. That's supposed to be an F. That looks like two P's. All right. So that's what we were talking about on Friday. Okay. This first question is kind of our first example of a problem to do with the law of conservation of energy. So when I drop something, okay, I'm holding it out the window and I've got it in my hand. Does it have any kinetic energy at that point? But it has potential, because if I drop it, it'll fall. Okay? That potential energy, as soon as it starts to fall, the potential energy will start to decrease, and what will start to increase? The kinetic. But what won't change? The total energy, right? The total mechanical energy won't change, because as potential decreases, kinetic increases, and they always add up to the same number, and that's why this statement here is true. Okay? The amount of mechanical energy was fixed. I carried that object up the stairs, put X amount of work into it, okay, let's say 200 joules, and held it out the window. Okay? It can't have more than 200 joules at that point. Once I drop it, that's it. It can't have more than 200 joules of mechanical energy, because that's all the energy I gave it. Okay? But what's going to happen is it's going to go from having 200 joules of potential to having less and less of that and more kinetic, until when it gets to the ground, it's going to have how many joules of kinetic energy? 200 joules. Okay. So if we're looking at this water balloon here, this 10 kilogram water balloon that would probably injure someone were it to fall on them, because that's 10 liters of water weighing approximately 25 pounds. Yeah. You wouldn't want to be under that water balloon. That's a beach ball. Okay, full of water. All right. So we drop this thing and we say that initially it's got mechanical energy. At the end it's got mechanical energy. Okay. Then we write this out. We say initial potential plus initial kinetic equals final potential plus final kinetic. Okay? And our job at this point is to decide, do I have all 4 of those forms of energy? Okay? And the answer in this question is no, I don't. Okay? We said that at the beginning, the water beach ball is being held out the window, probably with 2 hands. Okay? And it's not moving, so it doesn't have any what? It doesn't have any kinetic energy initially, so we can get rid of that. Okay? And since the ending point for this question is on the ground, it doesn't have any what at the end? Any potential, right? All right, do I have a formula for this? Yes, I do. M times G times H initial equals, do I have a formula for that? Yeah, 1/2 MVF squared. All right, I skipped a really important step. What was it? Right, collect the givens. I didn't write those down. Okay, so our givens are the mass is 10 kilograms and the initial height is 12 meters. All right, so I've got HI and I've got M. I'm trying to solve for VF. So what do I have to move? Half of M, right? Can I cancel M? Yes, I can. In this case, I can. All right, and I still need to do one more thing. Square root. All right, so VF is going to equal the square root of GHI, okay, over 1/2. Okay, so that's going to mean 9.81 times 12 over 1/2. Okay, now when I punch that into my calculator, okay, I'm going to go 9.81 times 12, okay, divided by 0.5, gives me twice that number, and then I got to square root that. 15.3 meters per second. Okay, is that ringing a bell from Friday? Okay. I want you guys to try number 12. Alright, so on this one I've got a 30-kilogram child on the trampoline who jumps vertically into the air at an initial speed of 1.6 meters per second. Alright, so we know already VI is 1.60 meters per second. Calculate how high the child will rise. So I'm looking for H final. Okay, now, any work being done other than, is there any work being done in this question? If I just jump off, it doesn't matter if I jump off a trampoline or if I jump off the ground. Okay, is there any work being done? No. My energy when I leave the ground and the energy I have when I'm at my highest point, there's no work done in between those 2 points. Only gravity is pulling on me then. Agreed? Okay. So, my initial and my final mechanical energies are the same. Okay. At the beginning, okay, EP initial plus EK initial, okay, equals EP final plus EK final. Now, some things we have to understand about the flight of an object. Okay, when this person leaves the ground, we're going to say the trampoline is one of those ones that's at ground level and there's a hole underneath it so you can jump. Okay, I don't know if you've ever seen those, but okay. What's their initial potential energy? 0, because they don't have any height. They're at the ground, right? So they have no initial potential energy, so I can cross that out. But they do have initial kinetic because they've got this initial speed here. Now, at the highest point the child will reach, how fast are they going? No, that's how fast they're going when they leave the trampoline. But now they're going to fly up in the air and they're going to slow down until they stop. At their highest point, they're stopped. Okay, that's one of the things about the flight of an object we have to understand. Whenever something flies up vertically into the air, okay, at its highest point, it's not moving vertically anymore. All right, so that means then that this here is actually what? 0. All right, so our initial kinetic equals our final potential. Now we can plug in our formulas. 1/2 mvf squared equals m times g times, whoops, sorry, that was supposed to be initial, equals mghf. All right, I want to get hf by itself because I want to find out how high the child will fly. So what do I need to move? M and G, right. Will M cancel again? Yes, it will. All right, so I've got 1/2 of VI squared divided by G equals HF. All right, so 1/2 times 1.6 squared divided by 9.81. Okay, well, they don't get very high. About that far. Okay? But if you only jumped at a speed of 1.6 meters per second and you're accelerating downwards at 9.81 meters per second squared, you're not going to be in the air very long. Okay? That's like credit card vertical kind of territory. Okay? Like you can barely see light under their feet when they jump. All right? Everybody with me on that one? So our final height is 0.13 meters. Okay, is this making a little bit more sense? Because we're going to crank it up a little bit here now. Okay, we're going to start working with problems that have all the kinds of energy at both points. All right, so we'll have a little more stuff to fill in here pretty quick. All right, so we talked about this one here the other day, okay, the average force of 100 newtons pulling back the bowstring, okay, and we talked about how if I do 100 newtons of force over half a meter, that's 50 joules, and that's how much potential energy would be stored in the bow because that's how much work I did, and that's how much kinetic energy the arrow would have because it's part of the bow and arrow system, and when I release the bow, it can only do 50 joules worth of work on the arrow, okay, and then how much potential energy would it have if it was shot straight up in the air? Well, 50 joules because that's all it was put into the system. Okay, looking at this diagram over here with the pulley. Okay, if I release that system, what's going to happen? Let's say that right now I'm holding the 2 kilogram mass, and I take my hand away. What's going to happen? It's going to, yeah, the 2 kilogram mass is going to accelerate down. What's the 1 kilogram mass going to do? It's going to accelerate up. Okay. Now, obviously, to get this system to this point, I would have had to lift the 2 kilogram mass up. Agreed? So I would have done some work on the 2 kilogram mass, and as a result, the whole system. All right. When I release this, can this system ever have more energy than what I put into it? No, it can't. The law of conservation of energy says it can't have more. Let's say I did 200 joules worth of work. It can't have more than 200 joules worth of energy in it. Okay? When this begins to fall, it had some potential energy, and it's going to turn into kinetic. But what has to happen to this? This mass has got to move up, and its speed is also going to increase. So the potential energy and the kinetic energy of this object are going to increase. Where's that energy going to come from? Exactly, from this mass. Right? This mass is not going to fall like it would fall if it wasn't attached to this one. Right? It won't fall as fast because it has to pull this one. So some of the energy from the 2 kilogram mass will go to this. It'll be transferred to this. The whole system can never have more than 200 joules worth of energy. Right? Doesn't mean that certain parts of it can't gain or lose to each other. Right? But the system as a whole can never have more than 200 joules worth of energy. You guys follow me there? Because sometimes we look at a situation like that and we're like, well, there's more energy in the system. There has to be, because that one block is going to gain both kinds. It is. But the other block won't. It'll lose some of its energy to the 1 kilogram block. Okay? But because they're attached, the whole system would still have the same amount as it started with. Okay? Everyone kind of with me there? It's kind of a weird one, but okay, it doesn't happen very often. You certainly wouldn't get a question on that. Okay? That's more of a physics 20 kind of a question. Okay. I want you guys to try number 13. Okay? And watch for this trick here. Our mass needs to be in kilograms. So how many kilograms is 20 grams? Nope, 0.02. 0.2 would be 200 grams, right? Kilograms is 1,000. Right? There's 1,000 grams in a kilogram. So if there's only 20 grams, there's 0.02 kilograms. Okay. So this is more like the easy ones that we did on Friday, the kind of entry-level ones. Okay, so we'll give you a few minutes on that one, and then we'll look at this pendulum question. All right, let's have a look at number 13 here. So we got this 20 gram dart, 0.02 kilogram dart, fired from a dart gun with a horizontal speed of 4.1 meters per second. Okay, and we know the mechanical energy of the dart is 0.481 joules. Okay, calculate the gravitational potential energy of the dart. Well, what two things do I add together to get mechanical energy? Potential and kinetic, right. All right, I want to find the potential, so what do I do with the kinetic? How do I move it over? Subtract it. Yeah. So I got EM minus EK equals EP. So I'll take my 0.481 joules and subtract 1/2 times 0.02 times 4.1 squared, and that'll give me my potential energy. 0.3129 joules. Okay, be my potential energy. So that's just reminding us how we calculate mechanical energy. That's the sum of kinetic and potential. All right, the second problem there was about a pendulum. Okay, so a pendulum, really simply, is a mass that can swing back and forth along a fixed path. So it's either on a mass on a string or it's on a rod. Okay, you've seen them in old grandfather clocks. This is what happens when you cut money from education. Okay, you get a drawstring from a hoodie tied to a roll of electrician's tape. Okay, that's what we can afford. And both of those came from my house. Yeah, okay, so that's what happens. Okay. All right, so it swings back and forth, okay, along the same path. Now, to start a pendulum, usually what you do is you just pull it up to a certain height and then let it go, okay, and then it swings over that path. Now, eventually it's going to stop because in real life there's drag and stuff like that, and it'll just quit, okay. But if it was in the perfect physical world, it would continue to oscillate essentially forever, okay, back and forth, back and forth. Now, what is it constantly doing here besides moving and oscillating? Okay, if I was to keep it going, what kind of energy does it have here at its highest point? Potential. And what does it have down here? Kinetic. Okay, it's constantly changing kinetic energy into potential energy and back and forth, back and forth. It just keeps doing that over and over and over again. Okay, it's just an example of a device that converts one form of energy into another. Okay, so it's got a 500-gram ball suspended on a 50-centimeter string. So they're really just messing with you a lot here with the units. Okay, we need our units to be in kilograms and our distance or height units to be in meters. Okay, the ball is pulled horizontally up a total vertical distance of 10 centimeters, 0.1 meters. Okay, at the bottom of the arc, the mechanical energy of the ball was determined to be 0.491 joules. What was the speed of the ball at the bottom of its arc? Okay. The pendulum is still above the ground at the bottom of its arc. Agreed? But can it fall? No, it's attached up here. Okay, so it can't fall. So we're going to assume this is height 0, and that 0.1 meters is measured from that lowest point. Okay, so here's what we have to consider. Up here, at the highest point, all of the energy is potential. Okay, how much is there then, according to this question? 0.491 joules. Because they told us at the bottom of the arc, the mechanical energy was determined to be 0.491 joules. Well, that means the mechanical energy everywhere along that arc is 0.491 joules because the initial mechanical energy equals the final mechanical energy anywhere along that arc. The only thing that changes is how much of that 0.491 joules is kinetic and how much of it is potential. Everyone follow me there? Okay, so all they're asking us to do is find out the speed at the bottom of the arc. Well, at the bottom of the arc, all of its mechanical energy will be in what form? Kinetic, because that's where it goes the fastest and it can't fall any further than that. Okay, so I'm just going to say then that 0.491 joules equals 1/2 mv squared. And I'm going to solve for v. All right, so again, the math of these kind of questions is not difficult, right? I mean, manipulating that equation is not very difficult. But getting to the point where I knew that's what I was supposed to do is the tricky part. Because we had to understand that as that pendulum swings back and forth, its mechanical energy doesn't change, that when it's at its lowest point where it's moving the fastest, it's got all kinetic. At its highest point where it's changing direction and not moving, it's all potential. Okay, that's the stuff we've got to read into a question and see. Okay, that's that context stuff that we've been talking about. All right, so if I manipulate this, I got to divide both sides by 1/2 of m. And this time I have to bring m over because I don't have an m on the top, do I? So there's no canceling m on this one. All right, and then I got to square root that to get v. Okay, so I would punch in 1/2 of 0.5, okay, underneath, so 0.25 to 0.491 divided by that, and then square rooted will give me a speed of 1.4 meters per second. Okay. Questions on how that one works? Okay, a pendulum's between pendulums and roller coasters. Really, those are kind of the biggest examples, okay, of law of conservation of energy that you're probably going to encounter. Okay, so this is just talking about the pendulum here, so you have that in your notes. Okay, pendulum's example, like we said, of conservation of energy. When the pendulum is lifted to a certain height above the table, you have to do work. That's the input of mechanical energy into the system, is us lifting the it's called a bob, by the way. That weight on the bottom of the pendulum is called a bob. I don't know why. That's what it's called. Okay. When you pull the bob away from the bottom of the arc, okay, you're doing work on that. Okay. When the pendulum gets released, okay, it begins to swing, and potential energy is converted to kinetic energy, and the pendulum speeds up. Okay. At the midpoint, the pendulum's moving at its maximum speed. Okay, and all the potential energy has been converted to kinetic. All right. And then we have to remember also that at the highest position on either side, okay, we're just going to cross off the other and say either here. On either side, okay, the pendulum stops and has no more kinetic energy. Its potential energy equals, okay, its mechanical energy at that point. Okay. Is this making a bit of sense to people? Right. Now, you've got these questions on yours, right? Okay, in your notes package, I included those. Okay. So what I want you guys to do, okay, is for right now, you don't need to answer number 1 because we've got a bunch of definitions of that already. Okay, I want you to answer these. Question number 2 for sure. Okay, I want you to answer all A through G there, and then in a few minutes we'll go through them together. Okay, so let's just start with A through G on that for now. Sorry, before you answer those, something to think about here. This football is not being kicked straight up in the air. Okay, it's being kicked up and across. Okay, so that changes things just a little bit when you're thinking about the types of energy it will have at certain points. All right, so what answer could we write for every single part of question number 2? What type of energy does that football have at every single point that they mention? Mechanical, right? We could mention mechanical and be right. Okay, because it has mechanical energy at every one of those points, because mechanical energy is the sum of potential and kinetic. So if it has either one, it has mechanical. Okay, now that's a bit of a cop-out, okay, but it's also true. So what types of energy does the football have the moment the ball leaves the kicker's foot? So we're going to assume that he's kicking it off the ground. Okay, so he's just place kicking kind of a thing. Okay, what kind of energy would it have the moment it leaves the kicker's foot? It would be almost entirely what? Kinetic. Yeah, that would be where it's actually moving the fastest. Okay. What type of energy does the football have at a point halfway up to its highest point? Kinetic as well as and potential. It would have both because it's now above the ground and moving, so it would have both kinetic and potential. Okay. What types of energy does the football have at the highest point in its path? It has potential. Does it also have kinetic at that point? It does in this case because it's moving horizontally. Okay? He didn't kick it straight up in the air, so it followed an arc, okay, as they show here, which means that at this point it is still moving that way. So it does still have kinetic energy at that point. All right? It stopped moving upwards, but it's still moving from side to side. Okay? At what part of its motion are the kinetic and gravitational potential energy equal? Theoretically, that should be somewhere around here, but because it's moving horizontally, it would be hard to say for sure. All right. All right, and at what part of its motion is the kinetic energy the least? Probably where? At the top. Yeah, at the top would be the place where it would have the least. I mean, yes, it's still moving sideways, but it's no longer moving up or down, so it's going to have the least amount of kinetic energy there. All right, question G is one I've actually put on a unit exam in the past. Basically put a situation just like this one and made it a multiple choice question. Okay. Where is the total mechanical energy the greatest? Explain your answer. Well, I just put, instead of explain your answer, it was A, B, C, and D. Right off the kicker's foot, halfway from the kicker's foot to the highest point, at the highest point, everywhere. What's the right answer? Everywhere. Okay? The mechanical energy of the object doesn't change. It's the same all the way along. What does change is how much of it's kinetic and how much of it's potential. Okay? That's a very telling multiple choice question. All right. Okay, for number 4, ball is thrown vertically upward from the ground. It rises to a certain height and then falls back to the ground. Okay, analyze the graph below. I'm going to give you guys a couple minutes, and then I'm going to have you tell me what's wrong with those graphs. Because there's several things really wrong about those graphs. Okay, but you're going to look at them first. I'll give you a couple minutes, and then I think you'll be able to tell me what's really wrong with them. Alright, if we think back to when we talked about graphing, all graphs have to have labels on their axis. They've got to have a title. These graphs have that. But what don't they have? They don't have numbers. They don't have scales, which makes them completely useless. Because now they make us think that something that's impossible is happening. Okay? We would normally assume that on a graph, if we had height on this axis, that it would be getting bigger as it went from left to right. Agreed? Because that's generally what happens. So here's what this graph then is telling us. Potential energy increases with height until it gets to a certain height, and then as it continues to go up, the potential energy decreases. Really? How does something's potential energy decrease if it's getting higher and higher and higher? It's impossible. It has to keep going up. What's wrong with this graph is there's no scale. The scale should say that this is a height of 0, and so is that. Okay? Because when you throw something up in the air, it goes up, and then it comes back down. Agreed? Okay, so what we see then is that this would be the maximum height here in the middle. Now that graph makes a little bit more sense. Okay? But that's why a graph needs to have a scale. Otherwise, it'll lead people to misinterpret the graph like we just did. Okay? We don't want that. Everyone okay with that one? Same problem with the kinetic energy graph. Okay? The height here should say 0, 0, and maximum in the middle. Because if you throw something up in the air, it's going its fastest when it first leaves your hand, so it has the most kinetic energy. And then as it continues to go up, the kinetic energy has to go down, because it's going to be going slower and slower and slower as it gets higher and higher and higher. Okay? And then when it reaches its maximum height, it's going to start falling back down to Earth, and its potential energy, or sorry, its kinetic energy is going to start increasing again until it comes back to your hand. Okay? That makes sense? All right. Now, here's what we're going to do. We are going to look at type of question you might encounter on, let's say, a quiz or a unit exam about the law of conservation of energy. Okay? Copy this one down. Good example. Okay, so we've got this situation, a roller coaster. At the top of the highest point, it's 60 meters above the ground, traveling at 6 meters per second. A short while later, it is on that smaller hill that is 15 meters above ground level, moving at a different speed, an unknown speed. We want to be able to calculate how fast it's going at that point. Okay. So is the amount of mechanical energy here the same as it is here, assuming we're operating in the perfect physical world? Yes, it is. So is this a law of conservation of energy problem? I sure hope so, because I wrote its example 1, law of conservation of energy, at the top there. Okay? All right. So here's what we know. The initial energy is equal to the final, and that's mechanical energy. Okay? The thing we have to remember is that means that EP initial plus EK initial equals EP final plus EK final. So nothing new so far. Okay? We write that pretty much every time it's a law of conservation of energy question. Now we said that at this point our job is that we have to figure out what kind or kinds of energy it has at the beginning and at the end. So looking at the beginning here, it's 60 meters off the ground. Does it have potential energy? Yes, it does. It's moving at 6 meters per second. Does it have kinetic energy? Yes, it does. So I can't cancel either EPI or EKI. They have an actual value. All right. And at the end, it's 15 meters above the ground. Got potential? How about kinetic? I would assume most likely. They wouldn't be asking us to solve for its final velocity if it didn't have one. Okay? And most of the time at this point you're going pretty fast on the roller coaster. Okay? So that's again one of those context kind of things. All right, so all of these have a value. I'm trying to find VF, which is part of this. Agreed? Okay, how do I get that by itself right off the bat? Divide? Subtract, right, because I'm adding. All right, so that's going to mean EP initial plus EK initial minus EP final equals EK final. All right, and that should make sense. This is the mechanical energy. If I subtract the potential, I should be left with the kinetic, right? All right, so at this point now I've got to plug in the full formulas, right? Because I got to find VF. So I'm going to put everything in there now. M times G times H initial plus 1/2 mass times V initial minus M times G times H final equals 1/2 MVF squared. All right, so it's a lot of writing, but it's no new formulas. I want to get VF by itself. So what do? Right. I divide by half of m, right? I mean, on this side of the formula, all that's there is this multiplied by this multiplied by this. If I want to get VF by itself, I got to do the opposite operation, 1/2 of m. And according to the rules of algebra, what I do to one side, I do to the other. All right. Is m in every term? Did I give it to you in the question? I did not. Do you need it? No. In this situation, you don't. Because every single term in this problem is being multiplied by m. M can be any number I want, because it'll cancel off. Okay? Now, I once really messed with a class with this. Okay? On a unit exam, or was it? Yeah, it was a unit exam. I gave them a question like this, and I forgot the mass. I just forgot it, because I knew I didn't need it. Okay, when I was making up the question. Wow. Person comes up to my desk and says, Mr. Couder, you didn't give me the mass for this question. Oh, it's 500 kilograms. And they go back to their desk. A few minutes later, another person comes up. Mr. Couder, you didn't give us the mass for this question. Oh, that's 10,000 kilograms. Okay. They go back to their desk. Now, by now, people are looking up at me and going, that was 2 different masses. Oh, no. And another person comes up because they're really confused. Mr. Couder, what's the mass? 1 kilogram. Really? Yep. Okay. Yeah, they were totally screwed up. Okay, you don't even need it. You can cancel it off. Now, in the end, they could have plugged in whatever number I told them. I knew that. That's why I told them all a different number. Okay, I mean, I was being a little bit mean because they should have known that. But okay, I mean, I can put in any number I want. Okay, so remember that. Mass, you can leave it in there, and you can make it whatever number you want. Won't make any difference. Okay, you can make it 300 million if you want, but that's a lot of typing, especially since you have to put it in 4 times. Okay. All right, so I'm going to cancel mass because it's in every single term, and I wasn't given it in the question anyway. Now, I've become a lot nicer in my old age. I always just put a mass on there, just so people don't get afraid. Okay, or they forget. So I usually just put one on, but in the end, you don't need it. All right, now, Kyle did mention a minute ago that this is solving for VF squared, and I want to solve for VF, so what do I need to do to... Right, I got a square root. Okay. All right, so now we got a bit of number plugging here. Okay. All right, so we start out with GHI, so 9.81 times 60, okay, our initial height, plus the initial kinetic energy, so that's 1/2 times 6 squared, because that was our initial speed. Okay. Then we got to subtract the final potential energy, so that's 9.81 times the 15 meters of the smaller hill. And we're going to divide that by 1/2. Okay. And that'll give us the speed of the roller coaster at the end of the ride. Okay, so at the end of this ride, or at that point on the ride, the roller coaster is moving at 30.3 meters per second, which is pretty fast. It's, I think, just under 120 kilometers an hour. Okay. So you would certainly feel the wind rushing through your hair at that point. Okay. Everybody with me? That's as hard as they get. Okay, it would be impossible for me to give you a harder law of conservation of energy question than that. All right, now I'm not always going to ask for VF. I might ask for one of the heights. Okay, initial or final. Okay, it's really not a whole lot different. You just got to isolate one of the heights. Okay, but in the end, they all work pretty much the same. All right, tomorrow, okay, I will not be here because I'm at the zone track meet, so you'll have a sub. Okay, I'm going to hand out to you the worksheet that you are going to be working on. Now, the sub is going to start, though, with your quiz. I'm going to post that. Okay, you're going to write your quiz, and then he'll play the podcast, and the podcast will help you mark it. Okay, and then you'll hand him in, same as always, and then he'll play the rest of the podcast, which will be me going through another one of these kind of questions, okay, to kind of remind you how they work, right? And then you're going to set to work on this. You can do this one in any order you want, okay, because we've done all of this stuff. I would say maybe start with the conservation of mechanical energy stuff, because I think I tell you that in the podcast. That's 14 through 17. Okay, they're just like this question here. If you find the first one really, really hard, try a couple of the easier ones on work energy theorem or something like that first, and then come back to it. All right?